Welcome everyone. Today we will continue our discussion on geodesics. We will go over how short geodesics minimize length and why length minimizing curves are geodesics. To start, we need to generalize the notion of covariant derivative a little bit. If we have an open set U in Rk and a smooth map phi from U to M, which is not necessarily a chart, a vector field over phi is a smooth map V from U to Tm with the property that the projection from Tm to M composed with V equals phi. This is another way of saying that for any point t in U, V of t is a vector tangent to M at phi of t. For each j between 1 and k, there will be a unique map Vj that takes a vector field over phi and returns another vector field over phi that we call the covariant derivative in the jth direction with the property that it satisfies the Leibniz rule, where the derivatives are taken in the jth direction, and if we apply it to a vector field v tilde on M, it coincides with nabla phi star ej v tilde. The proof that this exists and it is unique is identical to the proof that the covariant derivative along a curve is well defined, so I leave it to you. These covariant derivatives satisfy a nice property that if we take the covariant derivative in the ith direction of phi star ej, it is the same as the covariant derivative in the jth direction of phi star ei. This will be a simple computation using charts and the fact that our connection is torsion-free. We use the letters t1, t2, and so on for the coordinates in Rk, and x1, x2, and so on for local coordinates in M with respect to a chart. In these coordinates, phi star ei is given using the chain rule by the derivatives of the xk's with respect to ti times the derivative with respect to xk. If we take the covariant derivative of this in the jth direction and use the Leibniz rule, we get this expression. Now, the partial derivative with respect to xk is a vector field in an open set in M, so dj of this can be computed using nabla, where we are using again our expression of phi star ej in local coordinates. We can then use this infinity linearity of the connection in the first coordinate to get this expression. It is a little complicated, but it satisfies a very nice property. The indices I and j play the exact same role, so we can simply swap them and reconstruct each of these steps backwards. This proves the proposition. Now at this point, I would like to warn you that in general, di dj is not the same as dj di. In fact, the difference between these two operations is what we call curvature, and that will be the topic of the next lesson. Now we go back to our Riemannian manifold. Pick a point P and take the exponential map at P. In the last lesson, we proved that the exponential map was a well-defined smooth map in a neighborhood of 0, and when restricted to a small ball, its inverse was a chart around P. It had the property that when we take a line in TPM through 0, the image was a geodesic through P. In this context, the Gauss lemma says that if we take two orthogonal vectors v and w, then when we take the differential of the exponential map at v and apply v and w to it, we get vectors that are again perpendicular to each other. In other words, the Gauss lemma is telling us that the exponential map sends spheres centered at the origin to spheres perpendicular to the geodesics passing through P. To prove this, we consider the map phi from minus delta delta times minus delta 1 plus delta to M given by the exponential of t times v plus sw. The quantity that we want to show is 0 is the inner product between the derivatives of phi with respect to s and t at 0, 1. To do this, we take the function f of t given by the inner product between the partial derivatives of phi at 0, t. We know that f at 0 is 0 because when we take t equals 0, phi is constant with respect to s. We want to show that f of 1 is 0, so it will be more than enough to show that f is constant. We take the derivative of f and apply the Leibniz rule for the covariant derivatives. Now for a fixed s, the curve phi of st is a geodesic because it is the exponential map applied to a line passing through the origin, so the second derivative with respect to t is 0. Now we use the property of the covariant derivatives we proved earlier. dt partial phi with respect to s is the same as ds partial phi with respect to t. To this expression, we can again apply the Leibniz rule to say that it is 1/2 of the derivative with respect to s of partial phi partial t times itself. Again, we know that when we fix s, phi of st is a geodesic, so its speed is constant, and the speed of phi of st is its speed at time 0, which is the norm of v plus sw. Here is where we use the fact that v and w are perpendicular to write this as the norm of v squared plus s squared times the norm of w squared. And the derivative of this with respect to s at 0 is 0, which is what we wanted to show. This finishes the proof of the Gauss lemma. Before we move further, we introduce an important definition. We say that a piecewise smooth curve is minimizing if no other curve with the same endpoints is strictly shorter. We will use the Gauss lemma to show that short geodesics are minimizing. More specifically, we will show that if the exponential map at P is a chart in a ball of radius delta around the origin, then for any vector v within this ball, the curve gamma v from 0 to 1 is a minimizing curve from P to exp of v. To prove that, consider another piecewise smooth curve alpha connecting those 2 points. I want to show that gamma v is shorter than alpha. I will assume for simplicity that alpha is also contained in this chart and leave as an exercise to figure out how to deal with the case when it's not. Now, using this chart, we can write alpha in polar coordinates, having a radial coordinate and a direction coordinate. When we take the velocity of alpha, it will have a radial component and a rotational component. By the Gauss lemma, these two are orthogonal, so the speed of alpha is the square root of the sum of the squares of the lengths of these two components. We use this to compute the length of alpha. This is going to be bounded from below by the integral of the norm of the radial component. This is also bounded from below by the integral of r prime, and by the fundamental theorem of calculus, this is nothing more than the final radial coordinate, which is precisely the norm of v. This happens to be the length of gamma v. This shows that alpha is at least as long as gamma v, with equality only if alpha is a reparametrization of gamma v. This proves the proposition, but actually we prove something much stronger. There is a unique minimizing curve connecting those 2 points, and that curve is a geodesic. I would like to point out that not all geodesics are minimizing. For example, in the cylinder, this is a geodesic, but there is a shorter curve connecting those 2 points. However, all minimizing curves are geodesics, and we will prove that by the end of this lesson. In the previous lesson, we showed that if delta was small enough, the map psi given by gamma v of t was smooth in this domain. To prove it, we use the flow of the geodesic vector field and then the homogeneity property of geodesics. With it, we can define a map theta from the same set of vectors to m times m as psi at time 0, psi at time 1. This function assigns 2 points to each vector. First, we have the base point of the vector, and then gamma v at time 1. This should be interpreted as the map that sends a vector to its start point, its end point. In fact, if we were working in Rn, this is exactly what theta does. We will show that theta is a local diffeomorphism near the 0 vector at P. We will use the inverse function theorem, so all we need to show is that the derivative of theta at this point is a linear isomorphism. Actually, since the dimensions match, we only need to show that such differential is surjective. Take an arbitrary vector v in TPM. With it, we can construct the curve alpha in Tm given by the curve of 0 vectors based at the points of gamma v. When we apply theta to alpha, we get gamma v, gamma v. This is because by construction, alpha of t is based at gamma v, and since these are 0 vectors, the endpoint is the same as the start point. When we take the derivative of this at 0, we get v, v. We can also construct the curve beta given by the straight line tv. All of these vectors live in the same vector space, so their start point is p, and by the homogeneity property, the second coordinate of theta beta is gamma v. When we take the derivative at 0, this is 0, v. What we have shown is that for any v, both the vectors v, v and 0, v are in the image of the differential of theta. Since all vectors in the codomain are linear combinations of vectors of this form, we can conclude that this differential is surjective, and by the inverse function theorem, the proposition is proved. This means that provided delta is small enough, theta restricted to the set of vectors of length less than delta based in the ball of radius delta around P is a diffeomorphism with its image. As a corollary, we can prove something very powerful, that for any 2 points x and y in the ball of radius delta over 2, there is a unique minimizing curve connecting them, and this curve is a geodesic. To prove that, we simply know that by the proposition, the exponential at x in the ball of radius delta is a chart that contains y, so we can apply the result that we proved at the beginning of the lesson. Now we are ready to prove the fact that any minimizing curve is a geodesic. Let gamma be a minimizing curve. Since being a geodesic is a local property, all we need to do is pick an arbitrary time t0 and show that gamma is a geodesic around that time. By the corollary we just proved, we know that there is an open set U around gamma t0 with the property that between any 2 points in that open set, there is a unique minimizing curve connecting them, and that curve is a geodesic. By continuity, there is a positive epsilon such that gamma of t0 minus epsilon and gamma of t0 plus epsilon are both in that neighborhood. If gamma is not a geodesic near time t0, we could take the geodesic connecting those 2 points and replace a portion of gamma with this geodesic. This would make it even shorter. However, we assume that gamma was already the shortest curve with those 2 endpoints, so the only possibility is that gamma was already a geodesic all along. And that's it for today. We show that minimizing curves are always geodesics and that short geodesics are minimizing, but long geodesics may fail to be minimizing. Thanks for watching, and see you on the next lesson where we will talk about curvature.